Alright, this is lesson 8.2 where we're going to tackle the topic of area between curves. Now you should know this already, but the definite integral produces a value or a signed area, which may be positive, negative, or zero. Okay? However, if you're actually asked to find an actual area, well, that area cannot be negative. Okay? So what I want to do today is talk about something called area between curves. And let me just show you this for a sec. Okay, you don't need to write this down. But you see I have two curves here. I'm going to label these, the blue one as f of x, the red one as g of x. And if I ask you to find the area between the curves, I'm asking for this area that I'm highlighting here in yellow. Well, how do you think we can actually go about doing this? Well, you're, I think, comfortable with finding just the area under a curve, right? So if I were to split this up, here's my function f of x. You are quite comfortable figuring out this area. Please say yes. Okay. How would we denote this area? Well, this is the integral from a to b of the function f of x dx. Right? Okay, good. What other curve do you see here? Oh yes, that parabola. Well, this is the function g of x, and I think you are quite comfortable figuring out this area too, right? The area underneath the curve is denoted by the notation, the integral from a to b of g of x dx. Now, I'm asking you for the area between the curves, and that's the highlighted portion in yellow. How would I figure this out then? Hopefully you can see that if I take this and superimpose it on this graph, notice if I put the two areas superimposed to, what's left over is what I want, and left over usually means subtraction. So the area between the curve is really the higher function, finding the area underneath that graph, minus the lower function. And sometimes this notation here can be combined and written as the integral of f of x, the higher function, minus g of x, the lower function, and then our notation with dx. And this gives rise to our formula for the area of a region between two curves. Look, the area is equal to the integral of a to b of f of x minus g of x times df dx. As long as f and g are continuous and f is always above or equal to g. Okay? In essence, do you remember how we did that topic of Riemann sums? We figured out like each rectangle, we multiplied or we added all the areas together of each rectangle. Well, that's what we're doing here too. So let me just take one slice or one thin rectangle. Let's just pretend it's this one here. Okay? That one thin slice, sometimes we call it as dx. It's our width. Okay? Now, that's this part. Well, how do we find the area of a rectangle? It's the width times the height. Well, how do we describe the height here? The height would just be, the function f of x, the highest one, minus g of x. And that's what we have over here. So really, once again, the idea of height times width, or Riemann sum, comes into play. The thinner these rectangles, or these like slices of bread, if you want to call it that, thin slices, the better it is. And of course, the integral, of course, is the actual accurate area of this picture. So sometimes people don't like to memorize the formula, but they'll say, hey, look at the top curve, right? The highest curve, that's like your f of x, minus your bottom curve, that's like your g of x. Now, that's with functions of x. What about this thing called functions of y? Well, can I talk about that in a moment? I'll come back to this, okay? But right now, let me do example number 1 first, and then I'll come back to this statement, and then we'll attempt to do example number 2, okay? So with example number 1, it says find the area of the region bounded by the graph y equals x squared plus 2. That's this parabola. And y equals x, that's this line, from x equals to 0 to x equal to 1. Okay? So you can quickly just say, oh, I know, it's the integral from 0 to 1, yes, and it's the top function minus the bottom function. Yes, that's correct. The top curve is x squared plus 2, minus the bottom curve is x, and then that's dx. So once again, top, and then bottom. Good. And then we can quickly do this by hand. X cubed over 3 plus 2x minus x squared over 2. And then we'll evaluate this from 0 and 1. I love plugging in 0. You know that already. Minus 0 plus 0 minus 0. 1/3 plus 2, that's 2 and a third, minus a half, that's 1 5/6, or 11 over 6. So the area here of the shaded region is just 11 over 6. Make sense? Good. Now, let me go back to this idea of functions of y now, okay? So let me go back here. So I'm going to draw a little picture. You can draw this in if you want as well. If you don't, that's fine. Just watch and listen. But what happens if I talk about functions of y? What does that mean? Well, that means I have a curve like this and maybe like that, okay? Where now it's no longer f of x, but this is f of y, and this one is g of y. And let's say I'm integrating from a to b along the y-axis. So the area actually is here. Okay, in this case, our slices of bread are no longer like this vertically, because you see it's a problem there where I can't stretch it to the furthest part. Oops. I guess I'll just undo like this. But because we're integrating with respect to y, our slices of bread are now horizontal. See? Slice, 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 slice. Where now the width, okay, the width is this dy, that's our width, but our height is now the difference between, yes, those two functions. In this case, the difference from the right hand function, the right side function, minus the left side function. That's why we have right minus left when we're integrating with respect to y. So for functions of y, this dy means we're doing horizontal, okay, horizontal slices of the dy. The dx up here, of course, means we're doing vertical slices of our region, or the pieces of bread. Okay? So we're going to use that in our example number 2, because it does talk about functions of y. But in addition to that, sometimes you actually have to find out where the two curves intersect to figure out the boundaries. I gave you the boundaries for example number 1. Made life easy for you. But this time, in example number 2, you have to find them yourself. Okay? So, find the area of the region bounded by this curve, x equals to y squared minus 3. Now, if you don't even know how to graph that out, think of that as a sideways parabola. Hopefully you remember 3 here. I'm just going to go quickly draw something like this. And then y equals x plus 1. That would be a nice straight line, looking like this. Beautiful. And now your job is to what? Figure out the, intersection points. Now, you can figure out the intersection points for x or y, but I gave you a hint. I said, can you give me functions of y? So, it's best if you can solve for y. To do that, of course, we should solve for x in this case with the second equation, x equals to y minus 1. And then we can make the two x values the same, so y squared minus 3 equals to y minus 1. Oh, lovely, lovely algebra. Ooh, my favorite F word. That's right, factoring. We'll solve and we'll get y equals to 2, y equals negative 1. And that seems pretty good. So here's 2. Well, I didn't draw my diagram very well, but that's 2. And negative 1 down here. That's good. Negative 1. So in essence, we're now trying to find the area between these two curves. And do you see why this time functions of y makes life much, much easier? I'll just show you what happens with functions of x. Don't copy this down. But look, functions of x are like this. Right? Vertical. Oh, interesting. Look what happened. The top function is always the blue one, but it becomes blue, and then it becomes red for the bottom function. So notice 2 different bottom functions. That makes life difficult. And that's why for this one, best not to do these vertical slices. And that's why we should use horizontal ones. What's great about the horizontal ones? Look, the right function is always the red one, and the left function is always the blue one. And that's why if we can use an integral from a to b, in this case negative 1 to 2, in this case dy, once again horizontal slices, much better. Our right hand function is the red one, which is the equation y minus 1, and our left hand function is y squared minus 3. We can then now go ahead and well, I guess I'll simplify this first. Y plus 2 minus y squared dy. And now we'll do the antiderivative. Good old lovely power rule. Oops, I don't need the integral sign here. Y squared over 2 plus 2y minus y cubed over 3. I'll evaluate that from 2 to negative 1. Ooh. It's no longer 0. No fair. I like 0. Nonetheless, we can do this. I think it's 2 plus 4 minus 8 over 3 minus 1/2 minus 2 plus 1 over 3. And if I do all this, I think I get what? In my head, I think I get 10 over 2. Double check my answer. Okay, so here is an example how we used dy, or functions of y, to help us figure out the area. Okay, the last one. Set up integral. So I don't want to actually calculate this time, just set it up. So set up integral for the total areas of the regions, and you may use a calculator. Hint, you'll probably need a calculator to do it. Okay, what's interesting about this lovely graph, or picture? Okay, 2 regions, yes, 2 different regions. So what else? Oh, you're thinking, here's the x cubed graph. Okay, so that's f of x. And then you see the parabola. Ooh, yes, g of x. And so what's so funky about this question? Ooh, 2 different areas. Yes. And what do we notice about those areas? A different top function and a different bottom function. Oh, right. So you should be expecting to set up 2 separate integrals. So let's go ahead and find the intersection points first. Okay, so we should find the intersection points first. We will make the 2 functions equal to each other, and in this particular example, you have to solve for x. I think it's good if we just use the graphing calculator for us. I think life will be a lot easier than using algebra. Hello, graphing calculator. Our 2 functions this time, x cubed minus x squared. And then, oh yes, negative x squared plus 4.1x. Graph. Find the intersection points. First one is first one's not there. Uh-oh. What's going on? Intersection. Oh, I know what I did. It found the intersection at 0, 0. Ha ha ha. I don't want that. I knew that already. Here's the next one. Okay, 2.025. So here we have the point negative 2.025 as the x value. And then the corresponding one past 0. Let's see if we can figure that out. Second calc once again. Choose number 5. Intersect. All our curve to the intersection point in the first quadrant. Dump the dump the dump the dump the dump. Oh, 2.025. Okay, good. So this x value is 2.025. Okay, so we can do this now because I am thinking about making my vertical slits or slices of bread, which means the integral will be in terms of dx. So looking at that part, I'm starting at negative 0.25, going to 0. My top function, x cubed minus x squared, minus the bottom function, the negative x squared plus 4.1x, and then this is dx. So that gives you the part in yellow. And I'm going to ask you now to write down the integral for the part in purple, and then hopefully your answer will be the same as mine. And if that's the case, that's great, and then it's time to go and practice. If it's not the case, figure out what you did wrong, and then go and practice. Okay, go. Step 2, I should say, is find the area. And the area between the curves is this one in green, plus the integral from 0 to 2.025. This time your top function is the parabola, and your bottom function is the cubic function. There you go. Okay. Now, by the way, just as a little note on the AP exam, if you're thinking about saving some time writing these things, by all means, because we denoted the x cubed minus x squared as f of x and the parabola as g of x, you could have just replaced this with, yeah, f of x minus g of x. That's perfectly fine. And then over here, this could have been replaced with, yeah, g of x minus f of x. That is okay as well. All right? Okay.